By the 1970s, we had so many new particles being discovered that it was just ridiculous. They can't have all been fundamental. We had a lot of proton lookalikes and neutron lookalikes, proton lookalikes, and neutron lookalikes. They had similar but not the same masses. The charges were like, maybe instead of being +1 for a proton, they were like -1. It was a bit random and idiosyncratic. And so they said, this is ridiculous. We can't have all of these things being fundamental. They can't be thousands of fundamental things, and there can't be thousands of fundamental particles in the universe. And that's how he created the standard model of matter. So the standard model of matter proposes 3 important things. Number 1, that protons and their lookalikes, protons and lookalikes, are made of quarks, which we've met before, like the up quark, down quark, and we'll meet some more now. Number 2, electrons and lookalikes are called leptons and are truly fundamental. And finally, that forces are mediated by particles, which is an interesting thought, isn't it? So, in order to understand number 1 a bit better, let's insert an example. We know that the proton is made of 2 up and 1 down quark. Now, an up quark, which we abbreviate as a U, has a +2/3 charge. A bit strange, yes. And a down quark, abbreviated as D, has a -1/3 charge. This actually works out if you sum it up, because we're going to have +2 on 3, +2 on 3, -1 on 3, and that equals to +1. Similarly, we can see that a neutron, which has a structure of down, down, up, that's going to be -1/3, -1/3 for the 2 downs, +2/3 for the up, gives us 0, which is the charge of a neutron. And so if we have the up quark and the down quark, and we've already mentioned that electrons and the guys related to the electron are fundamental, then we have our first generation of matter. So this is pretty much what the entire world, more or less, is made up of. So this is the most important part of the standard model, actually. This is the first generation of matter. So we have the up quarks and the down quarks. And we have electrons, and we have the neutrino, as we discussed earlier. These are quarks, these are leptons. Leptons just exist by themselves, really, and quarks have to be pushed together, either in groups of 2 or groups of 3, in order to exist. Now, realistically, this would have been enough to create the entire world. We don't need anything besides these 4 things. But for some reason, God gave us another 2 sets for no distinguishable reason as of yet. No one knows why we have another 2 sets of particles. So this is the second generation of matter, and we also have a third generation of matter as well. No one really knows why. Now, it might look a bit intimidating, but what I can tell you, rest assured, that pretty much these guys are all just the same. So up, charm, and top are all related. So the only difference is that charm So if you have a look at charm, they have the same charge, right? They're both two-thirds. And the spin, which is like the magnetic moment, it is the same as well. So they're both positively charged. The only difference is that the charm weighs a bit more than the up particle. So charm is just a heavier version of up, and similarly, top is a heavier version of charm. So the only difference, so it's just kind of, the charm is just a heavier and bigger version of up, and top is a heavier and bigger version of charm. Similarly, strange is a bigger version of down. The charges are the exact same, right? So the same thing, just heavier. Similarly, bottom is a heavier and bigger version of strange. Now, do these names matter? Top, bottom? They were literally just looking for two words that were antonyms. That's why they were charm and strange. There's nothing charming about this quark. It's just an identifier. They could have used poo and pee because they're opposites, or live and die. They were just looking for any two opposite words. There's no meaning to this up and down. They're not physically pointing up or down. Similarly, this muon here, as we mentioned before, muons are just basically like heavy electrons. They have the same charge. They're just, look at here, about 200 times heavier. So, and the other property, besides these particles being heavier, is that they're more unstable. So the major difference between a top quark and a charm quark is that top is heavier and more unstable. And you should know these off by heart. Now, the last interesting thing about the standard model of matter is that it treats forces as particles. So instead of forces just being forces, forces are explained as the exchange of particles, which sounds a bit weird, but we'll explain that in the next video. We offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com.